All right, so last time we introduced the class, there was a whole bunch of websites in the PowerPoint from last time's PowerPoint. Also had all those places to find things for this lab. Please go to lab next week. We're going to jump around a little bit in the book, but as you can see in the PowerPoints are the suggested reading assignments. That's also in the syllabus. And so today we're going to talk about embedded systems, and it will be a introduction to embedded systems. All right, so what are some of the things we're going to talk about? We're going to talk about what is it? You know, what are these embedded systems? You've seen them. You've sort of got an introduction in 319K. If you looked at your handheld game at the end of 319K, that was an example of an embedded system. It encapsulated all those components. On the other hand, what we're going to talk about today is some of the particular challenges and the design processes associated with doing. So what's an embedded system? An embedded system has a processor in it. So it's got a processor. Okay. And it's going to be embedded, okay, to do one thing. Okay. So we will see that the essence of an embedded system is a smart object. What does it have in it? We're going to talk about all the things that have in it, but if we were to make a simple definition, an embedded system has a computer in it, but it's dedicated for a particular application. All right. Some of the other names, cyber physical system, smart objects, Internet of Things. These are all similar type definitions, terminologies for, again, something that has a processor and a computer inside of it. So if you look around our world, they're everywhere. Okay? It's got a programmable computer, so in some ways it's similar to a regular general purpose computer because we program it and we buy it and we sell it. But generally the software in an embedded system, it gives it that specific application. So it's very important for us to look at how we program an embedded system so we can and generally what we're going to do is cut a lot of corners, and we're going to talk about those corners to optimize so that we can make the most money and save the most lives as possible. Okay. In our particular case, it's going to have a TM4C123. That's going to be our microcontroller. The same one we use in 319K. It's got a computer and it's got the I/O stuff. And so all the stuff you learn in 319K will apply to this particular class. Again, it does one thing. Okay, that means it's specific for a particular application. The software goes in ROM, or more specifically, it goes in Flash EEPROM. Electrically erasable, programmable read-only memory, and by and large, the user of the device isn't allowed to program it. So when you want your thermostat to become better, you will download from the manufacturer updates to your thermostat. You can't just pop in the keyboard and program your thermostat to take over the world. Okay, so an embedded system can be reprogrammed, but it's generally done in a very specific and exciting way. Again, the computer is inside. Now, sometimes I previously said that there was one thing. Well, it might be two things or three things, but in general, it's limited to just a few things. All right. So how is it different than a regular computer? You know what computers are. We brought 2 or 3 of them in class with us. Oh, you like my slide here? Anybody know what this is? I'm an old person. Seen that? Yeah, that's what Macintosh used to look like. Or how about this one? This one's even older. No, that's not quite as old as an Apple II. This is why we called it an IBM PC. Okay, back in the day, IBM used to make personal computers, and that's an actual IBM PC. The difficulty is if you look at the terminology. Right? If you look at the word microprocessor, What does that mean? What's a microprocessor? Well, let's break it into parts. Okay? What's a processor?
Something that processes.
Yeah, okay. So what's if I draw a box? It processes. Yeah, so the answer was it executes software. Okay? But if I looked in a processor, what would I see? 306 question. What are the pieces inside the processor?
Logic gates.
Okay, that's too deep. They say the answer was logic gates, and yeah, absolutely. But I'm going to build logic gates to build which components? A little bit higher than logic gates I'm looking for. The ALU, yeah, sure. The arithmetic logic unit is the thing that does the add and subtracts and multiplies, divide, the shifts, the ors and ands. What else?
The bus.
Okay, actually, I'm going to draw the bus outside the processor.
Registers.
Registers, sure. Registers. What else? Yeah.
Cache of some sort.
Oh, too complicated. He said cache. Yes. We got no cache this semester, so I'm going to pretend it doesn't exist.
Darn.
No. But we are going to have 6 buses, though. So we'll be good that way.
Memory controllers.
Okay, it turns out, memory controller. Yeah, sure. The controller, the bus controller. Yeah, there's going to be a bus controller that the processor uses to communicate with the memory. Sure. We forgot the most important part. Yeah, this whole thing is the CPU. As a CPU is, he said CPU, and this is the CPU, and that is the actual control unit itself. The thing that's it's executing the instructions. All right, so that's a processor. And so a microprocessor is just a small one. Okay, so so an i7 is a microprocessor. Okay, and so the problem is, over the years, what a processor can do is exponentially grown, but the word has remained the same. So it's a very confusing word for us. Just to fill this out, what else do we got? Outside of the processor? Memory. What do we put in RAM?
Temporary variables.
Variables, sure. And you're going to go, trick question, what kind of variables do we put in RAM? Okay, what kind of temporary RAM variables do we put in RAM? Where else could I put variables, by the way? No, I can't put variables. I could put, okay. Actually, this semester, you could put variables in ROM. If you got like a high score list, you want some, you want to do some black box recording, and you want to restore. You can actually store into the flash ROM. But generally, we don't. When we're writing programs, we don't put variables in ROM. Where else will we put them? 312. Yeah. You're going to put them in the registers, because we got a boatload of registers, right? We got 13 registers, and you got, when was the last time you wrote a program with more than 13 variables in it? Yeah, not long. Yeah, so we're going to put them in registers. What else do we put in RAM? One more important thing.
The program you're computing?
Okay. Welcome to, the answer was, where's the software go? And the software is going to go in here, because it's an embedded system. And in every other computer, you put and on this laptop, the software is in RAM. But this semester, we're going to put our software into ROM. So it will, when we turn the power on, it will become whatever it's supposed to be. One more important thing.
Stack.
The stack. The stack has to go in here. You could have the heap. But those are the things in RAM. Okay. Yale Pat had a PhD guy doing a defense, and he built this really awesome computer with 45 processors, and it looked like this. And I said, Yale, this is the most useless computer I've ever seen. It literally looked like this. And I go, Yale Pat, nobody's going to buy this, right? What's missing? This is the useless computer. I/O, yeah, sure. Yeah, and that's the focus of this particular class is inputs and outputs. All right. We can think of embedded systems in the application space, in an automobile, for instance. If we looked inside of a car, would we find any computers? Yeah, we're going to find a lot of computers, depending on how new your car is. Anywhere from 20 to 50 computers are going to be in your car. Right, everything from the door locks to the electronic ignition to the safety. And it turns out the architecture of the computers in a car is, if these are all computers, what am I trying to draw here? How do you connect computers up together? A network, right? We need a network. And it turns out that this is a CAN bus, control area network. You're going to see this in 445M if you make it there. You'll see the CAN bus. So these computers will exist on a CAN bus. It's a high-speed, high-reliability, reliable network for connecting it up. And then we're going to need what? We might need to bridge the networks together, and it's a fairly complicated. And so that's what it looks like inside a car. We'll see a cell phone in a moment. The point is, there are billions of these microcontrollers on the planet, and there are more microcontrollers on the planet than there are people. Okay, now some of us hog a lot of them. You and I probably have got 100 of them in our life that are yours. Some people don't have quite as many. Okay, here you go, 300. Yeah, that's probably where if you looked at everything you did, from your watch to your cell phone to your television to your car to your elevator to the traffic lights, we interact with lots and lots of these devices. Okay. Which means that somebody has to make some money. Yeah. So out there is your opportunity to engage the world in a very, very significant way. So we can look at the typical block diagram of an embedded system, and that is we're going to have inputs, which are going to be connected to an input port. Types of input ports. What could I do? When I say input port, what do I mean? Okay, I heard USB. I'll get to that. What'd you say? GPIO. That's the general purpose input output, and you probably meant GPI, right? We're talking about inputs. Yeah, USB. USB is input or output, by the way, and so is GPIO. What else? SPI. Sure. Synchronous, we'll do that. UART, we did that in 319K. JTAG's not an input. I'm going to draw JTAG on here because it'll be very important for you. The joint task something group. I don't know. A stands for something, but J stands for joint. Group is the last one, and it's our it's debugging. It's our debugger. JTAG gets its own bus, by the way. That's how important it is. Okay. More? Okay, yeah, boring. Okay, you have my permission to forget about I2C. It doesn't work. And we'll talk about that when we get there, but it's a crappy interface. More? I2S. Oh, yeah, that one, that's the sound. Unfortunately, I don't know why our processor doesn't have I2S. It's a way to do multimedia. This this microphone is an I2S device. It's an audio multimedia sound protocol. Ethernet? Yeah, you guys are getting. I'm going to call Ethernet not an input port. It's more of a. It falls like in the CAN to be a connection. So Ethernet, CAN. We saw what the purpose of CAN was. What was the purpose of CAN? in the previous slide?
To link microcontrollers.
To link microcontrollers. So the purpose of CAN was to link microcontrollers together. The purpose of Ethernet is the same thing, just to connect computers together and not to gather information into your device. So this is input information we're going to bring into the computer. Important one. Just think your 319K labs. What are you missing? The ADC. Sure. And it turns out these are all crappy because you haven't seen the best one yet, and that's time. And when we get there, we will see that time is the most powerful media for which you to gather information. It is why there are billions and billions of microcontrollers in the world, is because there are a large amount of facilities to measure time, to affect time, to do time, time is, and then we're going to do processing. And this is your 312 stuff. We're going to do processing. That's the computer. That's the software. And then we got outputs. And all of these are outputs as well, except for this one is not an output. And we're going to have the DAC as an analog output. All right, so these outputs really, all these GPIO, USB, Ethernet, not Ethernet, UARTs, I2C, these are all examples of. And then when we connect it up with the internet, then we're going to call it a Internet of Thing. And so when we see our lab 4, you're going to have your microcontroller sitting here, 123. And then on top of that, we're going to put a Wi-Fi booster pack. And that's going to be Wi-Fi. And Wi-Fi is our connection, or one of the ways we can connect into the internet. The other one being, well, another way that we can take a computer and connect it up to the internet. Ethernet, right? Okay. So some fancy words in the world of internet is ubiquitous computing. What does Christine Julian call it? If you looked up Christine Julian on her webpage, she's famous for what? Here at the University of Texas? It's not just software. She does special software, really special software. It's called mobile computing. So she's off in Italy on sabbatical this year, but if you're interested in that here at the University of Texas, she's a great resource. All right, so what do you got to do? Okay, what are the big things for you to do? One of the things that I'm not going to teach you because we got a course on it, and that is, do you remember on my picture here, if I go back and I draw the microcontroller, which is the computer with I/O, and we have the embedded system with inputs and outputs. And then I asked, we want to make it smart, right? It's a smart object. Right? 'Cause that means it has software that does something smart, something powerful. How else could I make decisions? If you were, what other class have you taken that allow, other than 319K and 312, other than software, how do you take inputs, make decisions, and affect outputs? What else could you have done?
Logic design.
Which one?
Logic design.
Yeah, sure. You could have learned your logic, right? Your 316 and your EE 460M, right? And skip the software altogether, right? And use something called a field programmable gate array, right? That looks a lot like a microcontroller. It's got inputs, it's got state, variables, and it has outputs, and it runs and affects the world, okay? And so you will find in the world of embedded systems, well, I'll tell you, what's good about software? Yeah, software is is the most flexible. Let's go with that. You said easy to change. I'm going to write flexible. Flexible, I can't spell it, but you know. Flexible with however you're supposed to spell it. Any other advantages of software? Tell me about complexity. How big is software? On a scale, okay? What's the largest program you've ever written? Smart guys out here. Somebody's written a big one. What's the smallest program you've ever written, right? Yeah, to 10 lines, right? Okay, so we'll write 10. So 10 is the maximum you can have. Now, how big? Just for a scale of things. If you looked inside of your, something complicated, cell phone, or inside of your, inside an engine controller, inside a pacemaker, or inside of something complicated. Just give me a sense of. Okay, well we'll do this. Who's written 100 lines? All right, good. Who's written 1,000? Yeah, see, you're getting me. Who's written 10,000? 10 lines. Yeah, see, we're getting there. Few are still saying 100,000. Okay, 1 million. 10 million. So where I'm going is, what's their limit? There really isn't a limit. Now we, in this semester, only have 256 kibibytes of ROM. And if it takes about 2 bytes per instruction, you can see that, 2 bytes per instruction. We got about 100,000 opcodes we can put in this particular processor. But this is a little one. We could certainly put more. Okay? As opposed to digital logic, how is it better? How is 312 a better way to do things than, remember the traffic light controller you had in 319K? Could you have done that with digital logic? Yeah.
The board would have been like this big.
No, it wouldn't. The traffic light controller in 319K would have been just the same. It would have been an FPGA, and it would have been the same size. Okay. So, in what ways is it better? It's faster. Oh yeah, sure. It's fast. And it's fast in just sort of what basic principle makes digital logic fast? Well, everything runs in parallel. Is there another reason?
He doesn't have to fetch instructions. It does everything immediately.
Doesn't have to fetch instructions. Yeah, sure. I guess so.
In DSP, they replace things.
Yeah, sure. Yeah. It's sort of continuous. Is that what you're after? Now, there are 2 types of digital logic, and can you tell me what they are?
Application specific.
No, I'm taking synchronous and asynchronous. Synchronous logic basically fetches instructions and runs on a clock. Another thing about why it's faster? Yeah.
I have a question.
Okay.
Is one cheaper than the other?
Oh, the question was cost. They're both expensive. Let me give you, so in onesies, right, if you want one of something, then the microcontroller is cheaper because how much did you spend on your board? $13. Is anybody taking 460M? Do you know how much that board costs?
Like 100.
Yeah, 100. Yeah, or 80. Okay, 13. But that's for one. Once you get into mass production, then the price can be driven down however you want to go. There's really not much. All right, but the point is they're not the same. You should learn them both, and you should use them both. Things that have to be fast and continuous and immediate you want to build a new, a very typical application is you've created a new I/O port, right? Remember all the list we had in the previous slide of all the different types of I/O ports? You need a new one. There's never been, you invented yourself a new, iNet or whatever you want to call it. That's often done in the initial stages as an FPGA. All right. So it's a mix of hardware, which is processors and microcontrollers, and as we see later will be analog circuits, and software. And so when you program an FPGA, do you remember how you did it? Those who haven't done an FPGA program, what do?
You write code.
You write code. So, hey, what's up? I thought that we were doing digital logic. Well, you write code. And once you get into a class like 360R, which is digital integrated circuit design, then you take that design and then you translate it actually to transistors. And then it becomes cheap. Okay, so the FPGAs are a prototyping way, and then when we want to mass produce it, we'll convert it over into transistor logic. But the point is, the system is often not centered around the processor itself, but centered around the application. Okay. We're going to do a lot of low-level stuff, in this class. I've already mentioned 445M. If you want to learn about real-time operating systems, that's the place you want to go. And if you really don't like embedded systems and want to learn about operating systems, and that's the Yarabali course. All right. Big picture for today is this issue of designing within constraints, and we've got a slide for that coming up. Another big picture for today has to do with lives are at stake. When your code doesn't work, people die. And I'm sorry to say that each one of us, the insurance company, has given a dollar value to our life. And it's a little bit crude, but it's realistic. So I'm not saying you will never kill somebody in your job, but I will say that it should be done with great sadness. And when there is great risk, that incurs what? Well, you should work, but what it incurs is responsibility. That's what I'm after. So, because, if Windows goes blue screen, everybody's mad, everybody's sad. But if your automatic braking system goes blue screen, you hit the wall and bad things happen. So we're going to have to deal with this whole, how is it we prove it? The other constraint that we'll see over and over again is power, and I'll talk about that in a minute. Speaking of power, you shall not go into an interview. Okay, sidebar. You're going to go out and get a job. Okay? Maybe. Or if you go to grad school, you'll eventually get a job. Before you go to that job, would you please review your 411 and your 302? You'll be surprised how many people don't get jobs because they forget what Ohm's law is. So you won't pass this class without knowing the differential equation associated with a capacitor and inductor, because not that it's really critical for this class for you to solve differential equations, because remember, really all you need is algebra. But I need you to be ambassadors for the world. Okay, so as a review, as you know, P equals I times V. And this goes to the power dissipated in our system, right? That's the number of watts, and the different ways. Oh, that's misspelled. Okay, if we have a resistor, then we can think of it in terms of I squared R, or if we have a resistor, then it's V over R. If we multiply power times time, this is in watts. Power is in watts. If we multiply it times time, we get joules. This is important because that's what you get when you buy a battery. This is what costs money when you buy it from the electric company. Energy, right? Power times time. And so if we look at the relationships of energy, which is P times T, which is equal to I times V times T. How do I save energy?
Run it for less time.
I can reduce the amount of time, okay? And so it turns out you can put the processor to sleep, shut everything off, save energy. Right? That's the way most stuff works. What else could I do? I wanted you, okay, how do I do, he said reduce the power. Yeah, fine. How do I reduce the power? Look at the equation.
Higher resistance, lower the current.
Okay, it turns out the resistance is actually the resist. If you look at a digital circuit, the resistance is a function of the technology, right? Whether your MOS technology, your bipolar transistor technology, and so if you change technologies, you can affect resistance, which you'd want it bigger. Okay, but if you can't affect resistance, what's the next one? Voltage, right? And so if you think about what's the difference between a 3-volt system and a 1.65 volt system, what's the energy? Question?
So you said if you increase resistance, your power consumption goes down?
Yeah,
I thought it was the other way.
because the voltage. No, see if I look at this one right here. If I'm running at 3.3 and I increase the resistance, I change technology. I feel like if I go from a, okay, you guys are, I don't know. What's that? That's a BJT, bipolar junction transistor. What's the input impedance of this? Crappy, right? Kiloohms. What is this? Sorry for my crudeness. An N-channel metal oxide semiconductor. I forget which way the arrow goes. Okay, fine. Diode. Yes, it's a very crappy picture. But what's the difference between a BJT and an NMOS? Impedance, right? In other words, how much current goes into the base? Bunch. How much current goes into the gate? Virtually none. Impedance went up. Power goes way down. This is why all our digital logic is done with MOS field effect transistors. Okay, so where was I going? So what's the difference between these two voltage? That was a great question, by the way. Good question. Did I answer it?
Yeah, you did.
Okay, good. What's the difference between 3.3 and 1.65? How much did I save, assuming I have the same technology? How much less energy? How much longer will the battery run? Not twice. 4 times. Look at the old squaredy guy right there. Okay, so if I have a fixed technology, the impedances are the same. And by and large, every time I drop the voltage in half, I drop the power in 1/4. So that gives us to this power budget, and we'll see this later in the semester. And that is, if I look at a battery, okay, battery. If you buy a battery, do you know how it's spec'd? Okay.
Amp hours.
Yeah, it's often spec'd in amp hours. And I'm just going to throw it, but it's at a certain volt. It's at a certain voltage. So I'm going to put a volt amp hour in front of it. And now what did I just draw? What is, if I multiply volts times amps times time, that's energy. So when you buy a battery, you get a certain amount of energy. And so now what I want to know is how long, right? And so the energy power budget, it's called a power budget, but it really should have been an energy budget. But that's the world here. And so I'm given a certain number of volt amp hours in the battery, and now I have, this has to be greater than what the system power is times the lifespan. Right? So this is the power budget, the constraint around which we run. Okay? It's called the power budget. All right, so now, basic stuff, okay? Remember we talked about looking up a data sheet of things you know. What's Ohm's law? We'll do some easy ones here. V equals I times R. Okay, so that's an easy one. Now the question is, when will it explode? I give you a 1,000 ohm resistor, and if you put enough, voltage into it, it explodes. Right? Works away for a linear, and then boom, and then out here, right? It's got no, it's already exploded. It can't drive any current, right? So that's the nonlinear part. What am I talking about here?
The power rating.
This is the power rating. Okay, so if I have a, I'll do a quarter watt because that's easier to do the math. Okay, if I have a quarter watt resistor, what does that tell me? 0.25 watts. Okay, that tells me that it's already 1,000 ohms. What do I need to do here to get these to get the units match? I got watts here. I got ohms there. What do I need? What do I need?
Current.
Current square. So it tells me the maximum current that I can drive before it explodes. All right. And we just got one motor lab, and you won't put any resistors in series with it, so it won't be too bad. What's the equation for a capacitor?
V equals C di dt.
V equals C di dt. Is that right?
It's off the top of my head.
Yeah, is he right? Phone the audience, poll the audience. I equals, that's the inductor one, yeah. And it's, there's actually an easy way to tell. You'll remember when you get to the motor lab, what blows the motor up is the IDT, and it's the inductance, by the way. If we looked, again, I'm trained in a computer science field, so everything to me is simple. Capacitor is either open or short. If you look at the DC analysis of a system, the capacitor behaves like what? Open. And if you look at high frequency AC, what's that cap do? This comes a short. So you can look at a circuit and say, how will it pass DC? How will it pass AC? And then in between, obviously, we can look at the impedance as a function of the frequency, 2 pi FC. All right, capacitors. JW. All right, what about inductor? Okay, we already got the inductor equation, right? V equals L di dt, which means inductors don't like changing current. We're going to see the inductor in our motor, which will actually be modeled this way. This is the equivalent 3-element model for our motor, and it will have an inductance in it, and it will not like that change in current. Okay? And so, we can a very simple circuit looks like this, and we can blow stuff up with this circuit. All right, so we got the microcontroller here. If you want to blow up your lab partners, if you want to blow up everybody's computer on the bench, this is what you can do. All right, so I'll put a resistor here so I won't blow that transistor up. And so when this output is high, this transistor comes on. You got a VCE drop across this transistor, and we get an amp. I equals 1 amp. And the motor is spinning. Well, you know what software likes to do? Change. So if this thing becomes low, this transistor goes off. The VCE, well, the ICE goes to 0, Here the VCE is low and current flows. Now the current goes low. Well, let's draw current versus time. And how fast is the BJT? Switching time for a BJT on the order of nanoseconds. 10 nanoseconds, say. Now what happened? What did I just draw? Slope, right? So what is the IDT?
Very negative.
Well, yeah, it's not, negative isn't the problem. Right? 1 amp over 10 nanoseconds. Very large. Multiply it, say by a millihenry, which isn't that small, right? So this is 10 to the minus 3. This is, nanoseconds are 10 9, so that's 10 to the minus, this is 10 to the plus 8. And so I just created 1,000,000 volts. Now it's actually, I should have, to be more realistic, let me make this 10 to the minus 6. Let's make it a microhenry and make this more typically. We're going to get 100, 200, 300, 1,000 volts right here. That's a problem. We'll fix it. We won't let you blow up each other's stuff. What about an inductor? How does it behave in a DC? It's a DC, it's a short. And in AC, it's a open. Okay. And you should know what its impedance is in terms of, in the complex domain, 2 pi J, right? Did I forget the J in the other one? I might have. Right, I might have forgot the J in the J, 1 over J 2 pi FC. 1 and over here there's a J. And these are not things to forget. 2 pi FL. All right. We will do later in the semester diodes, BJTs, MOSFETs. All right. I mentioned this word coverage last time because we want to test it. There's a class for that. So we're going to talk about it more as we go further. But suffice it to say it's important. There's a cell phone. There's a bunch of FPGAs in here and a bunch of microcontrollers. I think 6 computers. Some of them M's, some of them A's, ARM A's. I got 2 more minutes. Let me summarize. This is like 6 ways to say the same thing. Let me summarize. Let me introduce the most important part of what's left, and this is the nature of what's real-time. Real-time is the fact that embedded systems will react to response. And so if we define the time between an event and its solution, that's called latency. And if we have a if the train is coming into the intersection, that's a problem. That's an event. The question is, how fast does the gate close? And in a real-time system, if you miss the deadline, people die. If you miss the deadline, don't bother. Right? The train's already passed. No sense putting down the gate. And so this will be very, very important for us to deal with responding. Okay. Hi. Next, let's talk about some of the specifications associated with an embedded system. First is it's important that it be small size and low weight. This is a constraint that we're often lived with. As mentioned before, it's important for the system to be low power. So we'll look for ways to make our system use less power. Often, our device has to operate in space, underwater, in an automobile crash, on airplanes, and so we have a very harsh environment in terms of the mechanical and electrical stresses exposed to our device. And as we mentioned earlier, when something goes wrong in an embedded system, somebody might die. And so it's often very important for us to consider safety during the design. And in order to make money, we're going to have to find a way to produce something at a lower cost and sell lots of it so that we can produce a profit. We mentioned what a microcontroller was earlier, and the one we're going to use in this course is a TM4C123. Most of the pins on the device are I/O ports, input, output, analog, and as I mentioned, many of these pins can be used for both time input measurements and time output. A real-time system is one which has a bounded latency. That means when an event occurs, a crisis develops, the system must recognize that crisis and respond to it. So we have an event and the response to that event. In this, latency is a critical parameter, and a real-time system has a latency which always works. In other words, once the airbag goes, once the engine decides that a crash has happened, there's a finite amount of time for it to recognize that a crash has happened before it deploys the airbags. Okay? So we must not only get the correct answer, but it's important to get the correct answer at the correct time. And we'll see this over and over in our embedded systems. Some of the specifications will define bandwidth, which is how fast will it process in bytes per second. How much power does it require, how small it is, how much it weighs, what the accuracy is. And surprisingly, much of the profit, much of the success we have in our embedded system will actually go according to whether or not people think it's beautiful, whether they love the idea, whether they interacts with them. And so there will be some subjective qualities of our system which will make a big difference in our success. In this class, like I said, we're going to use a TM4C123, but in general, you could use lots of different processors. And so we look at what the computer has to do. First and foremost, it processes data. Does it need floating point? Does it need 32-bit? What does it need? What is the number and the type of I/O devices? We listed them earlier. Somebody said they were interested in I2S, that's the sound one. If you need I2S, get a computer with I2S support. RAM, which is where our variables will go, and ROM, which is where our programs go. We have to figure out how big will our program be. Will it be 10 lines or will it be 10 million lines? And so that'll go a long way to deciding how much ROM we need. How big it goes has to do with the package. We talked about as you reduce the voltage, the power goes down. So can I run at 1.5 volts? And if I could, then my system will be a lot less power. All right. In order to build it, we need tools, and most manufacturers will give you a compiler and a debugger and some boards like our Launchpad. But a very important part of choosing a processor will be the plethora, the availability of starter software. Ideally, starter software that it looks just like what we want to do, and that'll get our ramp up. Be very close. Okay, so what do you do next? Go ahead and read up through chapter 2.7 in the book. And so in summary, we talked about what an embedded system is. We mentioned this real-time thing over and over again. It's going to be on the test, by the way, and that is a bounded latency between an event and a response. And this will be very important for our embedded system. It has to be reliable, which means we have to test it. Often we got to live within very, very tight constraints. It has to be done tomorrow, and it has to be small and cheap and all that sort of wonderful thing. And remember that you are indeed engineers, and so I need you to know what voltage, current, power, energy is. I need you to understand what a resistor, a capacitor, an inductor are. And again, we are working through the beginning part of the book. So what's next? Next, we're going to dive into fixed point. We're going to go on to the graphics associated with Lab 4. But anyway, have a good weekend, and we'll see you next week.